Hi there, welcome everyone. Welcome to this afternoon's virtual meeting. I'm just waiting a little bit longer. We've got 65 people signed in at the moment. There's 237 registered. We'll just keep going a little bit longer. Okay, a minute more. And there we go. We're at 4 o'clock. We've got 78 people online, and I guess it's time to start. Hi everyone, thank you for joining us today. My name is Jackie Morton and I've helped to organise this virtual meeting on behalf of the Royal Society of Chemistry's Atomic Spectroscopy Group. Welcome to everyone who's joined us this afternoon. This is our first virtual meeting and therefore I'd really appreciate your understanding for any mistakes we make in the presenting. The mistakes will be entirely all mine and I apologise in advance. Today's meeting is entitled A is for Arsenic and we have 4 speakers. Professor Julian Tyson, Dr. Priya Mondal and Dr. Laurie Savage, as well as myself. The format of the meeting will be that each presentation will run sequentially with one speaker after the other, and at the end we will collectively answer any questions that you might have. Please feel free to type any questions into the questions drop-down box on the GoToMeeting menu. There is a chat option as well. I'm not quite sure of the difference. I do know that the questions will be how I'll be able to answer them. And if you want to direct us a question specifically at one of the speakers, then please could you put Julian or Priya or Laurie or myself as the start, or simply 1 to 4, and we'll get the gist and try and get the right person to answer the right question. So today it's a great pleasure for me to introduce the first speaker, Professor Julian Tyson from the University of Massachusetts in Amherst. Julian received a bachelor's degree in chemistry from the University of Aberdeen in 1971, followed by a PhD in analytical chemistry from Imperial College in 1975. He was a faculty member at Loughborough University in the UK from 1976 till 1989, when after that he relocated to the University of Massachusetts, Amherst. He retired from his full-time teaching positions at UMass in 2016, but continues to pursue some of his teaching and research interests. Today, Julian is going to talk to us about tracking the analytical chemistry of arsenic. So let's see if the first one works slickly. Okay, here we go.
Thank you, Jackie.
Okay, you're welcome.
And good afternoon to everybody. So what you're looking at right now is a photograph of the University of Massachusetts Amherst campus. And I'm sorry to say that there is no building visible that we could call the chemistry department. The prominent building in the foreground is actually the Arts and Humanities Library, and the slightly larger grey building that's breaking the skyline is a multi-science building that contains some chemists, but also physicists and astronomers and mathematicians and so on. Chemistry is actually spread over 6 buildings now, as I guess a trend that we occupy different buildings for different functions. But as Jackie has indicated, I started my scientific career at Aberdeen University, and then eventually ended up at the University of Massachusetts Amherst after a large number of years. I'll let you do the math. But the reason that I'm sort of qualified to give this sort of opening talk is that if you look at the Web of Science, there are about 30 items in the Web of Science that have the words arsenic in the title and the name Tyson in the list of authors. The earliest publication from our group was in 1992. The total publications altogether is 230, and about 30 of them are related to arsenic. The publication numbers are swelled by the fact that I've written a large number of reviews over the years, approximately 41 review articles and about 10 book chapters, which I guess are sort of reviews as well. And in amongst all of those are 35 atomic spectrometry updates, to which I've been the co-author, published in JAS, as I'm sure you're all aware. And as you will probably appreciate, writing all of these reviews means that I've read a lot of papers, and so I have some qualification to address you about what's going on. So in terms of tracking the analytical chemistry of arsenic, is a dictionary definition. I'm using the Web of Science to pull the data. So I'm put the word arsen with the wildcard and the words analysis or determination into the title. Unfortunately, we seem to have lost the distinction between analysis and determination, so you need to search on both. Get 4,755 hits. But if you remove the word arsenazo, which I think is some kind of spectrophotometric reagent, it drops by about 200 and something. But if you add in speciation or variations thereof, the numbers jump up to 5,000 or nearly 6,000. And I've tracked these on this graph here. We're used, I think, these days in time of COVID to seeing plots like this. So we could describe this as two waves. Maybe you can see the papers that have speciation in the title started to separate out around about 1989, 1990 maybe, and therefore they now account for a significant contribution to the overall analytical chemistry of arsenic. Now, I thought I would try to find out why there was this significant increase from about 1990 onwards by looking at some more details of the title words in the Web of Science. So if you look at the papers that have got the word water in the title, you see the plot on the left-hand side. Put rice in the title, you see this plot on the right-hand side. So they don't necessarily account for the large increase in the numbers of papers that we're seeing. Same is true for soil, sort of modest increase. If you look at words that have the letters BIO at the beginning of them, then there's perhaps more of a significant trend upward for these. But so those words, you can run your eye across this list in alphabetical order here. So we seem to be in a sort of alphabetical theme for these meetings. All of these bio words appear in a title of something to do with the analytical chemistry of arsenic. And in the interest of time, I'm going to click on to the next slide, because really I think why we're seeing such a sort of significant increase is that it's just the range of materials that people have now become interested in measuring the arsenic species or the total arsenic concentration or both in. So again, alphabetical order, you can run your eye across this list of materials that appear in the titles of articles, and therefore it's difficult to sort of roll them up into sort of broad categories, which people don't tend to use in the title when they're just publishing a paper about the analysis or the determination, I should perhaps say, of arsenic compounds in olive oil, for example. So again, I'm going to move on. So one of the other things that I have noticed over the years, and I have written about this previously, is that one sees lots of papers in the literature describing essentially the same analysis. And I think it's reasonable to ask the question, why do we see that? So the most obvious answer is maybe the method is not quite right in some way. People are finding ways to improve the performance of the particular method. That's against criteria such as detection limits, speed, cost, so on, accuracy and precision. Or, as I perhaps be a little more cynical here, but I do want to make a serious point as we're going through this lecture, maybe the referees are not doing a very good job of reviewing manuscripts that are being presented as candidates for publication, or maybe researchers aren't checking the literature to see what has been previously published, or both. And I'm going to come back to that theme as we go on. I want to focus specifically on the determination of inorganic arsenic in rice, a topic that's sort of near and dear to my heart. We're still working on this in my post-retirement years, trying to develop simpler and simpler non-atomic spectrometry procedures. So it doesn't really fall in with the, at least my methods don't fall in within the titles of this particular talk. We need speciation information, and as you probably know, Hplc ICP-MS is a very popular procedure. So one might ask, why Hplc? And I'm going to give you all the negative attributes here because I'm not a great fan of Hplc in this particular application. Hplc chromatography is slow. Oh my goodness, is it slow. It dilutes the analyte. Gradient elution leads to compound-dependent responses, which have to be handled, and some species are difficult to separate. We're dealing mostly with anion species, but if you have cationic material in your mixture, which maybe there is in rice, they run at the solvent front of an anion exchange separation. So just to remind you about the analyte dilution, one doesn't often hear people discuss this very much or see them discuss it. But if the injection volume was 50 microliters and you had a flow rate of 1 ml a minute and a peak base width of 1 minute, then it's easy to calculate that the elution volume is 1,000 microliters. And if the concentration were uniform, that would be a 20 times dilution, 50 microliters diluted across 1,000 microliters. But if you have a triangular shaped chromatography peak, the dilution is 10 times at the peak maximum. And of course, that gets worse for smaller injection volumes and larger elution volumes. So just bear that in mind. And why ICP-MS? Again, I'm not a terrific fan of this technique for this particular analysis. Chloride is a problem, as many of you probably know. Argon chloride has the same nominal mass as the monoisotopic arsenic that one measures with ICP-MS. Carbon causes ionization enhancements and has to be dealt with somehow. Mobile phase composition often interferes, can degrade your sampling and skimmer cones. So you probably need a DRC instrument. You need some way of buffering the carbon concentrations across samples and standards. Most instruments suffer from enough drift and compound-dependent responses that you need some kind of internal standardization, which many researchers add to the mobile phase or to the sample, or via post-column flow injection, or both. And so there's the need to calculate response factors in explaining what the calibration strategy has been. So now let's look at progress in this particular analysis. So here's a paper from 2001. This is a popular chromatography column. It's an anion exchange, PRPX 100. And the appropriate conditions are written down the right-hand side of the slide here. And a relevant performance parameter, the detection limit in the solid rice material. I want to draw your attention to the time that it takes to do this analysis. So the important part of the chromatography is out here somewhere. This analysis takes about 9 minutes or so before you can re-inject another sample for analysis. Let's move on to 2005. Actually, we seem to be going in the wrong direction in terms of analytical performance here. Maybe an improved detection limit, longer column for some reason. But now we've got a 12 minutes analysis time. So if you want to do lots of rice samples, this is not necessarily the way to go. We move to 2012, same column, slightly different dimensions, but probably the first sign, if I can say that, of real progress. Now we're down to sub 4 minute retention time, but that was achieved by running the chromatography at 40 degrees C. So you have to have the ability to do that. Not many labs seem to be invested in running the chromatography at anything other than room temperature. The other feature about this particular method was it used malonate as the mobile phase, and that seemed to be a significant improvement over phosphate, which is the more popular one with the other researchers. So here we go at 2021, a full 20 years after that first paper that I showed you, and despite spending a lot of time talking about the optimization of chromatography, these researchers still have got an analysis time of about 8 minutes or so. Though they're using this longer column for some reason, but the flow rate has been increased to 1.4 mils per minute. So there is a role for flow rate, and these researchers, in fact, do discuss it in some detail. You could shorten the analysis time by increasing the flow rate. You could perhaps program the flow rate in here to cut down this time in here. But of course, when you're dealing with a nebulizer-based instrument, if you increase the flow rate above what the nebulizer is happy with, you're going to decrease the sensitivity and maybe therefore the limit of detection. And maybe increasing the flow rate is going to degrade the chromatographic resolution. And the peaks are going to get closer together, but maybe they're going to get narrower as well. So that's not necessarily an automatic outcome of the flow rate. This slide, I think, shows the real progress. Now we're going back to 2017. Notice now there are only 3 peaks plus an internal standard. The internal standard actually was arsenobutane, and it was added by flow injection post-column. And so that's why it appears at this longer time here. The chromatography is all over in 1¼ minutes here. So you'll notice now it's the same column, but now it's 50 millimeters. It's a decreased flow rate. It's got a small volume spray chamber so that we don't get lots of extra column broadening as a result of the regular size spray chamber. And we're no longer monitoring at mass 75 over here. We've got some oxygen introduced into the system. So we're monitoring or these researchers are monitoring at ASO plus. They also modified the procedure so that hydrogen peroxide was added. So now the arsenic 3 peak that would have been down here somewhere, maybe not resolved from this peak at the front end, would now be rolled up with the arsenic 5 peak here. So inorganic arsenic now just shows as 1 peak. That's a better strategy, I think, than moving this peak to the front by adding a reducing agent. And still, as you can see, the chromatography is over in 80 seconds or thereabouts. So let's just talk about method performance. Right, so a lot of effort goes into optimizing methods for parameters like limited detection, but in fact, for this particular analysis, limited detection is not really an issue. People want to be monitoring at the action level of inorganic arsenic in rice, which currently is 200 ppb for those countries that have got that kind of limit. We might in the United States roll out something at 100 ppb. Who knows? The US FDA is pretty slow in responding to the outcry over this problem. But as you saw from all of those previous methods, detection limit's not a problem. Neither is accuracy, as it happens. Of course, all this talk about interference effects, but in fact, most researchers manage to avoid peak overlap. They use appropriate calibration procedures. They demonstrate accuracy by the analysis of certified reference materials. There are several certified reference rices that are certified for the species content, and most people will do spike recoveries of the various species. And in this regard, most published methods are okay. Precision can be an issue, and I want to take just a moment or two to talk about this, because if we're making measurements around an action level, then the issue of false positives and false negatives becomes relevant, and we need to know how precision might affect that situation. So on this next slide here, I want to draw your attention to an article that I think is well worth reading. But if you're not in the water analysis business, you may not have thought that this had anything of interest. So this paper in Talanta way back in 2002 is a good read. It's well written, and it's got a very interesting plot that I'll show in a moment. Just a word about what is a positive result and what is a negative result. So my strong recommendation is that the analytical chemistry community makes that distinction with reference to the decision level. So if it were to be 100 whatevers, then 105 would be a positive result, and the result of 95 would be negative. But we should bear in mind that the public are hearing a lot about testing these days, and it's not how COVID-19 tests are described. The situation is the other way around. Anyway, in our universe, I hope a false positive is a sample that exceeds the standard. That's the 105 situation, when the real concentration is actually less. And a false negative would be a result that was recorded as below the standard value when the true concentration actually exceeds the standard. And this is the plot that I want to draw your attention to. So a little bit of a busy slide here, but it's based on a model for the way that the precision of the measurement varies as a function of the concentration, based on this paper by Mike Thompson and his colleague back in the Analyst in 1976. So the standard deviation at any particular concentration is equal to some constant value, the standard deviation of the blank, if you like, plus a multiplying factor times the concentration. So that's the basis of the model for how does precision vary with concentration. And on the box insert here, they've switched, unfortunately, from using S0 to sigma naught, but they're comparing two analytical procedures: a field test kit for measuring arsenic in groundwater and a laboratory-based analysis, that's the dotted line, for which the text of the paper shows you how they derive these numbers here. So this is the S0 value, and over here is the K value. And so what the plot shows that if the decision level is 50 parts per billion, which it is in Bangladesh and some other Southeast Asian countries, then if the real concentration is up here somewhere, say 60 ppb, then if you're using a field test kit, then there's about a 25% probability that you're going to get a false negative. That is, the test will actually show a result that's less than 60 ppb. But if you're using a lab-based analysis, which has got a much better precision associated with it, then you've only got a, whatever this is down here, 2 or 3% chance that you're making a false negative. And on the other side of the plot here, we have the false positive situation. If the true concentration was 40, your field test kit's got about a 25% chance of showing that as greater than 50, whereas your laboratory-based kit's got almost zero probability of showing you a false positive here. So it's well worth having a look at this kind of plot and how it was constructed, because you can do the same thing for your particular situation, and you can predict, therefore, knowing the precision of your procedure and how it varies with concentration, you can predict how many false positives and false negatives you're going to get at any particular decision level. Well worth knowing. So as I wrap up here, the optimization that you need to consider in producing a method like this is that you can't have the best limits of detection and a short analysis time with good resolution. And all of these things have to be considered. And as we don't need the best limit of detection, my sort of bottom line of this slide anyway is think fitness for purpose here. So in wrapping up, I'll reveal the identity of the paper that I think really has made progress in this area, the Jazz paper from 2017. But as I said earlier on, I'm not actually wedded to HPLC ICP-MS as the best way for doing this. So I encourage you to think of hydride generation, selective hydride generation as a way of doing speciation analysis, maybe coupled with AFS rather than ICP-MS. And here's a couple of papers here that might start you off thinking about the possibilities of those. And in any case, you should definitely read these two articles here, the critical review by Francis Coney and his co-worker back in the Analyst in 2004. And as I said, I've written about some of these things before. You can find this in this online journal back in 2013. And my last slide with the concluding remarks is so that as a researcher and author, please, when you write your manuscript on arsenic speciation analysis, discuss and explain the choices of the method parameters, and please give references to the prior work on which you're basing this, and state clearly what improvements you have made. And if it's a chromatographic improvement, let's have some plate numbers and resolutions to genuinely show some improvements. And if you're a referee or reviewer of a manuscript, then my sort of same comments apply, because I have self-interest at heart here. If I'm going to be writing about your work in a review article for an atomic spectrometry update, then I want to easily find what is new and what is true, and therefore review your paper in ringing terms. That's my final slide. Thank you very much for your attention, and I'm happy to answer questions as we get to the end of the meeting.
Okay, Julian, thank you so much for that. Like we said, we'll come to the talks at the end. And now we're going to pass to our second speaker of the afternoon, and that's Dr. Depriya Mondal. Dr. Mondal is an environmental epidemiologist with more than 10 years experience. Let me just, sorry, I'll start Priya's introduction again in a minute. I just need to work out how to, sorry about that, everyone. Okay, so Dr. Mondal is an environmental epidemiologist with more than 10 years experience working in the area of environmental determinants, especially arsenic contamination and human health. With an environmental public health background, Priya's areas of research include global health, epidemiology, toxicology, health risk assessment, and risk perceptions. Today, Priya is going to talk to us about arsenic exposure from food intake in endemic areas of Bihar in India. Okay. Priya, is your camera on?
Yeah.
Okay, brilliant. I will disappear and let you start your talk. Thank you.
Can you see my slides?
Yes, we can. You can start your presentation.
Oh.
Brilliant. Okay, thank you.
Thank you, Jackie. And thank you for inviting me to the Symposium A is for Arsenic. I'm going to talk to you about arsenic exposure from food intake and presenting some results from an ongoing study from Bihar in India. So I want to start with this very quick brief that arsenic exposure can cause many, many adverse health outcomes. And that is the reason that it is important to determine exposure in endemic populations. You can see that it can cause cancer. And I want you to note that in this picture, you can see these skin manifestations, which are caused by arsenic. And those are hallmark for arsenic-induced toxicity. Sorry. It's not letting me progress. I'm sorry, it's just not letting me progress on the slides. Yeah. So can you see the progression in the slide? Okay. So arsenic can cause arsenic is distributed very widely, as you can see from this plot. And even though this is an old and classic plot, but here you can see that presence of arsenic has been noted in all over the globe. That said, it is most severe in Southeast Asia, where more than millions of people are known to be exposed to arsenic. In fact, in India, it is estimated that 15,000 premature deaths are occurring each year as a result of arsenic exposure. In a recent news article by a civil society called Inner Voice Foundation, they have reported that around 10 lakh people, so which is 1 million, were dead just from arsenic exposure in Indian cities. So this is an important problem. I started working in this area of arsenic-induced toxicity or arsenic problem almost 15 years back in time. The only one thing that I have noted during this journey is that despite known solutions and technologies being made available, we still have people being exposed to arsenic problem and facing this situation where they are helpless and they are infected and there is no particular solution apart from going to the doctors or ending up in hospitals. So we started to look into a particular area in India, the state of Bihar, where we wanted to look if there is any particular food habit or any particular diet, along with lifestyle and social factors, that can help reduce the arsenic-induced toxicity. And why we wanted to do so is because though in India, the worst affected area or state is West Bengal, just next to Bangladesh, but Bihar is equally arsenic exposed, where the first cases of arsenic toxicity was recorded in almost 2003. And since then, cases are on the rise. We wanted to see if there is a particular food habit which can help this population combat or being more exposed to arsenic-induced problems. It is very, very common to see these arsenicosis symptoms if you are doing a survey in Bihar. And as you can see, these are all the pictures taken as a part of this survey. We performed household-based surveys, collecting samples from an adult male and adult female from each and every household, running questionnaires to understand their food habit and their dietary intake, along with their self-reported health status. We also recorded their socioeconomic status and other measures that are informative to understand the arsenic problem in their households. We did some anthropometric measurements, for example, looking into the BMI or blood pressures, etc. Collected some biomarker samples, for example, blood for clinical parameters, and most importantly, collected the samples for exposure assessment, which I'm going to take you through. So all these collections were done from 96 households from these known arsenic affected areas as shown in red within the state of Bihar. So we performed our sampling from over 19 villages spread across the sides of the river Ganges, as you can see from this plot, covering 8 out of the 13 red areas I have shown. So the 8 districts out of 13 in Bihar. This is the first result table, and here it shows the arsenic concentrations in the different medias we have collected and we wanted to look the exposure from. So the drinking and cooking water, raw and cooked rice, you might be able to see that arsenic concentration in cooked rice were relatively high, and especially in few samples, and we don't know why it is so. but I want to spend a few more slides on the arsenic in wheat grain and wheat flour, because this is the first study where we looked arsenic exposure from wheat and estimated the risk in the study population. So if you see in this plot, we have tried to compare the arsenic concentrations in the wheat grain from our study, which has a sample size of around 72, and compared it with published studies from China, Bangladesh, Pakistan, etc. And you can see the concentrations in this study are relatively low compared to that observed in previous studies from other parts of the world. That said, one of the interesting findings from our study was increased concentration of arsenic in wheat flour compared to wheat grain, even though from literature we knew that once the wheat grains are grinded, the barn is removed and the arsenic is removed with the barn. And almost 30 to 40% of arsenic is normally removed in the wheat flour compared to the wheat grain. But we found an increased concentration in the wheat flour in many samples. And at the same time, we also found, as you can see from the plot in the right-hand side, that there was a good correlation between arsenic in wheat flour with the arsenic in drinking water, as shown by the dark spots and the dark equation. So what was happening? We tried to explore a bit, and we found that in many a case, the villagers do soak their wheat grains in water, which can happen to be contaminated with arsenic, before they grind it to the flour. And this is the flour which is used for making these homemade breads, which is consumed every day. Almost 99% of our surveyed population said that they do take these homemade breads referred as or known in the areas as chapatis and rotis. So this was the way the arsenic was being taken through the wheat exposure. And indeed, if we estimate the risk using a probabilistic method, we found that there is a chance that 1 in 10,000 might have a cancer risk due to their exposure just from wheat intake in this studied population. Now, if we start looking into the risk from overall different food intakes, and in this case, we have looked into the arsenic from wheat, cooked rice, and also from potato, the vegetable which is consumed almost all through the year. This is interesting to see that the exposure from food intake is almost equal to the exposure from drinking water, even though slightly high, in fact, which is shown by the 2 bars on your left-hand side. But most interestingly, in this study, we found that if you have an arsenic exposure above the WHO guideline level of 10 ppb, in that situation also, food was found to be more important route of exposure, as can be seen from the 2 right-hand bars. And until now, we knew that food is only an important route of arsenic exposure in areas where concentration in drinking water is either low or there is no arsenic in drinking water. But this was not the case for Bihar. When we looked into the different food items, we did find that there were almost equal exposure from food, from rice and wheat intake, when arsenic was less than 10 in the drinking water, but rice was an important route of exposure, in fact, more than the wheat, when arsenic concentration in drinking water was more than 10 ppb. And perhaps there is some particular reason that the way they cooked their rice or the water they were using was contributing to the very high arsenic in the rice that they were consuming. It is also important to mention that unlike 99% of the studied population consuming wheat every day, it was around 75% who only consume rice every day. So there were 25% of the population who don't consume rice every day, adhering to their health cautiousness. If we look into the overall exposure, then we see that it was just less than 1 for this study population, again using probabilistic method. That said, around, if the 85th percentile was 3.49, Around 15% of the population had arsenic exposure above the 3 microgram per kg body weight per day, the recommended upper limit for inorganic arsenic exposure by the Joint FAO Food Additives Committee, based on the lower confidence limit for a 0.5% increase incidence of lung cancer. And this limit has replaced any other previous limits that we were adhering to in terms of risk and exposure assessment. Now, if we try to stratify our data by this recommended limit, we can see that those exposed below this limit had got equal exposure from water, cooked rice, and relatively from wheat and potato. But if those who had an exposure above this recommended limit of 3, their water is becoming the most important route of exposure, and that is when you have a high concentration in drinking water. This is just simply because the consumption of water is much more than the consumption of any other food items. And the overall risk estimated for this study population, again using a probabilistic method, was around 6 per 10,000, which is higher than the US EPA threshold guide for 10 to the power minus 4 to 10 to the power 6. And the 95th percentile for this study population was around 80 per 10,000. So indeed, food was contributing to increased risk in this study population. This is my last result slide, and I did mention in the beginning that skin manifestations are hallmark for arsenic toxicity. In our study population, whether it is keratosis or pigmentation or melanosis, we found that around 18% of the population had some form of manifestation. And in this last table below, you can see that those with some kind of skin problem had higher arsenic exposure, significant exposure from cooked rice, wheat flour, and potato. So food is definitely a problem in this area. So I would like to conclude by saying that along with mitigations and interventions focused on reducing arsenic exposure from drinking water, focus should be given on irrigation water as well as reducing exposure from food intake. With that, I would like to thank the entire team of NutriSam, the students who has been working in this project, and most importantly, the participants who participated. And thank you all for listening.
Thank you, Priya. That was really, really interesting. Our next speaker today is Laurie Savage, and let's see if I can sort that. Okay.
Hi, so is that...
Hi there, Laurie. So I will just turn that on. Okay. So Laurie is an analytical chemist, currently at the University of Aberdeen, is an analytical and environmental chemist and obtained his PhD from Queen's University in Belfast in 2019. He's currently working as a research fellow at the University of Aberdeen with a focus on arsenic exposure in Bangladesh. Today, Laurie is going to talk to us about atmospheric deposition of arsenic and the need to evaluate the contribution from natural sources. Okay, thank you, Laurie. I'll pass over to you.
Okay, thanks very much for that. And yeah, thanks for the opportunity to talk here today. So I'll be discussing the atmospheric deposition of arsenic, and in particular, I'll focus on the contribution of natural sources of arsenic in rainwater, so specifically biovolatilized sources of arsenic. I'll briefly mention my current work, which is with the Capable project. This is the Cambridge program to assist Bangladesh and environmental risk reduction. So it's a large multidisciplinary epidemiological based project. And primarily my role is to understand the total exposure of arsenic to populations of Bangladesh. So it focuses on cohorts in urban slum and rural populations. And the exposure source I'm looking at are rice, drinking water, and atmospheric particulates, so specifically PM2.5. As this work is still in progress, this talk I'll present data from my previous work on atmospheric arsenic and arsenic in rainwater. So this is work I carried out during my PhD at Queen's University Belfast. And the initial work I look at focuses on the collection and analysis of arsenic species in rainwater. So this includes seasonal studies in South Asia and a long-term, that's a 2-year daily sampling study in Northern Ireland. So at each study location, samples were collected daily and frozen immediately before being analysed in batches. So rainwater was analysed by ion chromatography for separation, and then coupled to ICP-MS for quantification. So while inorganic arsenic is frequently prioritised as a non-threshold carcinogen, when looking at atmospheric fluxes of arsenic, organic species are also relevant as indicate a biological source. But prior to this study, there was very little published data on arsenic species in rainwater. There was just one paper which reported very occasional low levels of organic arsenic. However, from the first samples that we analysed, we saw significant amounts of organic arsenic, significant to the total arsenic. So for the analysis, with the anion setup that we have, both trimethyl oxide, or TMAO, and arsenobutane are very poorly retained on the column. So the first step was to determine which species, or if both species, were present in the rainwater. So we carried out a simple spiking experiment. So rainwater subsamples were spiked either with arsenobutane or TMAO, and then analysed using an anion exchange column. The anion exchange chromatograms on the left show arsenobutane and TMAO co-eluting. They cannot be distinguished. These samples were then reanalyzed by cation exchange chromatography and are shown on the right. The cation exchange column has a much stronger retention of TMAO and can therefore be easily separated from arsenobutane. So this determines that the species present in the water is TMAO. TMAO is labelled here and is clearly separated from the arsenobutane in the middle chromatogram. So that large peak in the bottom chromatogram is the TMAO present in rainwater with the additional TMAO spike. This trial was essential for the confirmation of species present. So for the actual quantification, the anion exchange column was used as it gave better peak shape and sensitivity. So having consistent chromatography and low detection limits was a key factor for the study, especially over the 2-year sampling campaign. So detection limits for arsenic species was consistently below or around 10 ppt parts per trillion. So this summarizes the data for a whole summer monsoon season in Bangladesh. Daily samples were collected and the data is plotted here. This shows the arsenic sum of species concentration on the histogram, which is the right-hand axis, and then on the left-hand axis, this is a cumulative deposition of arsenic species. So it shows the sum in red, then black for inorganic, and then at the bottom there's the green TMAO line. The deposition of arsenic in rainwater was higher than expected. So 2.3 grams per hectare of inorganic arsenic and 0.4 grams per hectare of TMAO. And this is comparable to the uptake of arsenic in paddy rice. So this could be an important consideration in terms of food safety, especially in rice-growing regions that are not impacted by arsenic-tainted irrigation water. But it's also worth noting that TMAO is a considerable fraction of the total arsenic, meaning that biological processes are a major factor. So this shows the relationship between arsenic species and other elements. Because organic arsenic, predominantly in the form of TMAO, make up a significant proportion of arsenic in rainwater, the sources need to be considered. So in order to determine the source of TMAO in rainwater, the relationships between arsenic species and other elements were investigated. So we know the sources of volatile arsenic include fungi and bacteria in soil, or marine algae in oceanic environments. But while there's data for terrestrial emission of arsines, there's very little data on oceanic emissions. So these plots show Bangladesh summer monsoon rainwater. They also include winter monsoon data from rainwater collected in Sri Lanka. So the data selected here is for elements with a known marine origin. So boron, iodine, and selenium are trace nutrients that are either physically entrained from the ocean to the atmosphere or they're biovolatilized from seawater. So selenium is biovolatilized, boron is physically entrained into the atmosphere from the ocean, and iodine is likely to be emitted from the ocean via both mechanisms. If you have a look at the Bangladesh data first, the summary on the left, there's a strong positive correlation between inorganic arsenic and selenium, as well as iodine. There are also strong positive correlations between TMAO with selenium and boron to a lesser extent. And also to a lesser extent, there's a positive correlation between TMAO and iodine. However, there's no correlation between inorganic arsenic and TMAO, or between inorganic arsenic and boron. The Sri Lanka data showed no correlations between marine elements and arsenic species. However, there was a strong positive correlation between TMAO and inorganic arsenic. So this looks at the meteorology modelling. To understand these differences in rainwater chemistry between the Bangladesh and Sri Lanka samples, it's important to understand the meteorology. Very broadly speaking, the monsoon weather system in South Asia is binary, so it flips from northerly to southerly during the year, driven by warming and cooling of the ocean. So weather originates from the north in winter, so from continental Asia, and is generally much drier. And during summer monsoon, this weather system is the opposite and brings wet air from the oceanic south, so from the Indian Ocean to the South Asian subcontinent, bringing lots of rain. So this plot on the left shows a typical winter pathway of air from origin to the site in Sri Lanka. And the plot on the right shows a typical summer plot. This is the oceanic origin and pathway to the collection site in Bangladesh. The origin of each sample collected could then be plotted. So the red dots show the origin of the Bangladesh back trajectories, and the blue dots show the origin of the Sri Lanka weather back trajectories. And then other factors such as trajectory length could also be calculated. So taking all of this into consideration, principal component analysis could then be used to understand the interrelationship between the number of variables, including the chemistry and rainwater deposition and weather trajectories. So the loading plot on the left shows very different trends between the Bangladesh and Sri Lanka data, although there is commonality at the XY intersect. But generally the plots are different, and the ellipses are drawn out by the outliers in both cases. For the score plot on the right, the TMAO stands out from the other elements, suggesting a very different regulation. So the relationship between arsenic and elements in wet deposition is presented here by comparing the log concentration in seawater on the x-axis with log concentration in rainwater on the y-axis. The dotted line indicates 1-to-1 ratio. So it can be seen that those elements, sodium, magnesium, boron, iodine, that are physically entrained from the ocean are grouped together. It can also be seen those elements, the elements from anthropogenic emissions are grouped on the other side of the red line. So we hypothesize that the marine environment is the major source of TMAO, and here we can see TMAO clustered with selenium, an element that we know is biovolatilized from the ocean. So in order to test the hypothesis of a marine origin of TMAO, seawater was collected from nearby Belfast Loch and transferred to reaction chambers with Drechsel head and sintered glass bubbler. So air was drawn through the seawater via a low volume pump, producing a negative pressure. And at the inlet and outlet of each reaction chamber, there were silver nitrate traps to trap arsenic, arsenes emitted from the reaction chambers. So these are silica glass traps that are dosed with silver nitrate as per Mestro et al. In 2011. So to test the hypothesis of the marine production of TMAO, there were 8 reaction chambers. So they each had a litre of fresh water, and they're placed in a temperature and light-controlled incubator. So 4 vessels were amended with 1 nanomole dimethyl arsenic acid, so DMAA, after 1 week, and 4 vessels were left unamended. So it was a 2-week experiment. After 1 week, 4 were left unamended and 4 were amended with the DMAA. So all silver nitrate traps were changed after 1 week, and then 4 of the reaction vessels were dosed with 1 nanomole dimethyl arsenic acid after the week. So yes, I see that come up before. So the traps were eluted with boiling water and analysed. So I'll have a look at the data. So this is the production of arsenes from seawater. So for each of these plots, so it's arsene, non-methylated arsene in the top left, and then dimethyl arsene, sorry, in the top right, and then trimethyl arsene, and then it's the sum of arsenes in the bottom right. So the vertical red line is the standard error of the mean, and then it's the horizontal for the mean. This shows the production of arsenes. Sorry about this. Okay. Sorry, having slight technical problems. So inorganic arsenic and DMAA were found on the inlet, whereas inorganic arsenic, DMAA, and TMAO were found on the outlet. So the inlet concentrations are subtracted from the outlet concentrations in further calculations. So I'll just summarize the results here. So arsene was produced at a rate of 2.9 picomole per litre during week 1, but negligible during week 2, irrespective of the DMAA addition. And then for the DMA, so DMA is the volatile form of DMAA, was negligible for week 1 and week 2 without the amendment, but with the amended samples, the production was 15.8 picomole per litre per week. For the TMA, the production rate was 3 picomole per litre per week during week 1, and 8.3 picomole litre per week during week 2, without the amendment. And then with the amendment, it was 14.7 picomoles per litre in the amended vessels. So, as broad conclusion, the TMA is biovolatilized from seawater and is commensurate with inputs from wet deposition. So as input, it was important to see that it was the TMA was produced from the DMA spike as evidence of biovolatilization rather than physical entrainment, and corroborates the hypothesis suggesting that marine environments are a major source of organic arsenic. This is kind of the first tentative data, but much more work is required to estimate the contribution of marine-derived arsenes to the global arsenic cycle. So it's not possible to to make global estimates from this, as algal growth is not uniform throughout ocean. And then we have the effect of a warming ocean could potentially increase production of arsenics from the ocean. And then further work would be required to look at the contribution to receptor landmass, especially arsenic-sensitive paddy environments. And this is a reference to your work mentioned. So thanks very much for listening, and thanks to Jackie for arranging this and for I'd also like to thank everybody at the Institute for Global Food Security, especially Andy and Paul and Manus for this work that I presented this afternoon. And I'd also like to thank everybody at Tesla, especially Jürgen and Andrea, for the support with in my current role. Okay, thanks very much.
Thank you, Laurie. Let me just try and work the screen back out again, guys. So I've just got to change back to me. And okay, so hopefully you can see my screen now. And the final talk of this afternoon is for me, and I work at the Biological Monitoring Team at the UK's Health and Safety Science Research Centre in Buxton. My main research focus there has been the development of analytical techniques for the analysis of metals and their species in biological samples. And today I'm going to discuss arsenic speciation methodology and how we use this in the laboratory to better assess workplace exposures. Okay, so the talk outline will discuss how we currently analyse arsenic speciation in urine samples, what kind of data we see from routine biological monitoring, and some results that we've seen from some interesting cases in the last year or so. Okay, so this year celebrates 10 years of us doing routine arsenic biomonitoring for workplace exposures. Prior to that, we used hydrogenation coupled to an ICP-MS, but we were finding that it just the lack of specificity for an amalgamated arsenic result really wasn't helping with workplace exposures, and certainly couldn't differentiate between dietary exposures to compounds like oxonobutane and workplace exposure to inorganic 3 or 5. So in 2003 we started to develop a method at that time using Hamilton PXP100 anion exchange column, and then in later years we moved to using just a simple guard column, an AG7 Thermo Fisher guard column, and that's our current setup. If so, the picture is a little bit far away from seeing this. We use a one-fast ESI system, which is a simple switching valve, and we have a small 5cm column. And how the system works is we use an ammonium carbonate mobile phase, typically about 3 millimolars in concentration, and we run that as a constant flux through the column. We send the autosampler to take up the sample, which is a 1 in 30 diluted urine sample, and then after that, maybe a minute or two, we then send it to a second sample, which is mobile phase B, which is about 70 millimolar of ammonium carbonate. That enters onto the column and then flushes off the remaining 3 peaks for the analysis. And in this time period since 2011, since we've offered this as a commercial service, we've analysed almost 4,000 samples from workers, mostly from the UK. We validate this method using external quality assurance samples from GQAS, a German-based at the University of Erlangen EQA scheme, and we establish a background reference range for UK people. It's not a massive range. I think there's 95 samples in our range, but it was a place to start to help us interpret whether the results we'd see from workers, whether that would we could see exposure in it as a difference to a background reference range, and the reference for that range is just cited there. So as I've said, it's a small anion exchange. Actually, the column is described as having anion and cation capability. What that means, I've never really been fully sure, and the component of the Ag7 column isn't widely available, so we don't actually know what the substrate is. And we do know that that substrate changes from time to time, and that causes a little bit of flux with the method. I hope this method is satisfactory to Julian. It elutes all its peaks in 5 minutes, and these peaks are the ones we're mostly concerned about in our urine assessment for workplace exposure. So arsenobutane comes off in the dead volume. We work hard to separate that from the arsenic 3 peak, and then the second mobile phase, the 70 millimolar ammonium carbonate, takes off the DMA, the MMA, and the pentavalent arsenic at the end. You can see from the limits of quantification that these are low. Typically, they are somewhere around 20 to 40 nanograms per litre, and that's more than adequate for detecting in routine biomonitoring purposes. So where do our samples come from? So I looked at the data for the last 3 years, and most of our samples, as you might expect, come from semiconductor workers in the UK. Some come from the optoelectronic component, and a small amount come from manufacture, and the manufacture would be from glass manufacture or precision tool manufacturing. We have some hospital samples from some cases where they've reported a high total arsenic, and we also see some from universities, and then this patch here are from some overseas samples that we analysed, and I'll try and show you some chromatograms in a little bit of what we found in those samples. The results from recent review samples that we've done, these are based on creatinine corrected urine values, and these are the 90th percentiles that we've seen for these different categories of workers. The background range for the 95 people are along the bottom. And you can see, as you might expect, in semiconductor workers and in optoelectronics workers, where protecting the product is paramount, and there's a high uptake in the use of RPE and PPE. Now, all of the arsenic species are within the background range. We hardly ever see any exposure there. And obviously the one we're concerned about is arsenic 3 and arsenic 5, although sometimes DMA can play a part in trying to help us interpret exposure to higher levels of inorganic arsenic. We do see a little bit of exposure in the manufacturer's urine samples that get sent in, where we can see some elevated arsenic 3 and arsenic 5, and slightly over for DMA and MMA as well. And then these overseas samples, again, clocking up to be quite interesting, where we can see really quite significantly higher levels of both inorganic 3 and 5 and DMA and MMA, and actually no AB. And the source of AB is typically from seafood, although we can get some DMA from seafood and shellfish, but AB that low in this instant would suggest that they're not big fish eaters. So some interesting cases to talk about. The first one is a urine sample we obtained from, it was in last November, from a man who lives in Scotland and has a spring water's main supply to his house. Now in Scotland, 3% of domestic households have a private water supply, and as part of having that private water supply, they are tasked with maintaining it. And in this instance, whilst the man hadn't noticed any symptoms or any differences, someone also using a similar spring water supply had to have their water tested for work purposes. And so this And what we can see here is the chromatogram from the man who's has the private water supply, and we can see that he has a little bit of arsenobutane. He has some arsenic. Sorry, I'm just trying to move something out of the way. He has some arsenic DMA, and he has some arsenic 5 as well. And if we compare those with the background levels, we can see that his 3 and 5 are elevated, and his DMA and MMA are also elevated. When questioned a little bit more, the man did say that he had some irritation on his skin, and he hadn't linked that with any arsenic exposure. So following on from this, the man was asked to abstain from using the spring water for 1 month and then sample his urine sample again, which he did do. And so we see, sorry, see if I can get the next. There we go. This is after 1 month of not drinking the water supply, his spring water supply. We can see that the arsenic 3 peak and 5 peak have disappeared. DMA and MMA have returned to normal range. And in this instance, his arsenobutane has increased threefold, but we could put that down to eating some sort of sea fish, because there would be no other source really in a water supply from that. And if we look at these chromatograms in a little bit more detail, we can just zoom down on the to the bottom end, so you can see that in the top one where he's been drinking the well water, we can see 3 and 5, and where he hasn't been, we can see that 3 and 5 aren't there. We are still trying to follow up this case and to have a sample of the well water or the spring water to analyze also. But in the meantime, the man has informed the hospital involved that he's going back to using his spring water. Then I was going to talk about the 2 different types of overseas samples that we've been analysing, and one of those is from South African workers that I mentioned before, where we measured 150 urine samples. Now this was just at the start of last year, so January 2020, and we were supposed to follow these up. But a pandemic got in the way, and we've not been yet able to follow these samples up. But we think that these samples have come from South African mine workers. We can see that they don't eat a lot of arsenobutane. This is just a typical chromatogram, but they were all very similar. And we can see that the arsenic 3 and 5 in their urine and the DMA and MMA are very elevated. And this was typical for 80% of the 150 samples that we analysed. The second case is where we have some more contextual data, and these are from Nicaraguan sugarcane workers who are being investigated looking for a cause to their chronic kidney disease that occurs in sugarcane workers in the area. The workers as a whole had elevated total arsenic in most of their urine samples, and when we got to subsequently speciate a small 50, I think it was just 50 urine samples for these sugarcane workers, we came up with a problem that they all seem to pretty much have 50 parts per billion or 50 micrograms per litre of arsenic 5 in their samples. And the first instinct is to think, well, there's some contamination, maybe there's been some glassware where the samples are being sampled into, or there's been an added reagent that has arsenic 5 in it. So these samples were decanted into a cardboard vessel, and then from that vessel they were put straight into a plastic vial. Some of these vials had boric acid as a solid in the bottom of the vial. So we have analysed the cardboard vessel, we've analysed the boric acid, we've analysed the plastic tubes, and we don't find any arsenic in any of the tubes. So I'm afraid I have to leave this one slightly hanging as well, being we don't have an outcome for the source of the arsenic 5 peak in these workers. Enough to say that we are, it's being followed up in a second visit to Nicaragua to collect more samples, and including water samples. And so we should be able to, because one possibility is that every worker there is drinking contaminated arsenic water with arsenic. But I would expect that the variation in people and the variation in excretion of species would mean that they would have a variable amount of arsenic 5, and not all of them have roughly 50 parts per billion of arsenic. So it is a mystery that we need to get to the bottom of, and the team at Imperial that we've been working with at King's College are collecting further samples. The third case isn't really one case. It's to show you where we are with what we see on our Thermo AG7 column. Over the years, the column has got more specific, and we are able to pick up different compounds that we weren't able to see before. So sometimes we get this little peak that appears, well, little, it can vary in size, but between DMA and MMA. And it might look like not very much, really, but they do stand out, and we have got some frozen samples where we've got some bigger peaks. So this is 2 urine samples where we've both seen, and we've seen this little peak. And you can see that this one doesn't have a major dietary influx from seafood. This one really doesn't either, but that there are, in both these instances, arsenic 3 and 5 are present. If we add hydrogen peroxide, what happens in this instance is the peak disappears, and that's because we know that this peak is thiodMA, and that's because we had the thiodMA synthesized by Kevin Franscioni in Graz, and we were able to elute it off our column, react that with hydrogen peroxide, and so that's become the way of that we elucidate that this is thiodMA without having the standard readily available all of the time. And what also happens when you add hydrogen peroxide, as Julian mentioned, is you oxidize arsenic 3 to arsenic 5. And when you and what happens to this little peak here? Well, it oxidizes to DMA. So you get an increase in DMA and a decrease in the thiodMA peak. Now we also see a peak that occurs between MMA and arsenic 5 just here. So this is our 2 microgram per litre standard at the top, so you could get an idea of the elution of the peaks. And you can see here that this was a recent semiconductor worker where he has absolutely no other arsenic species to notice or to mention, apart from this peak that elutes between MMA and arsenic 5. And in the same cohort, this was a semiconductor worker from the same batch that doesn't have any arsenic 3 or 5 exposure either, doesn't have the unknown peak, and maybe has a bit of seafood in his system, maybe from a tuna sandwich or something like that. So we can see that this peak isn't there. So when asked further, this worker alluded to the fact that he eats these regularly on a daily basis. And so we got quite excited, thinking this peak occurs at in different samples over the years, and we've never been able really to work out what it is. So we've pre-concentrated it, we've taken to an LC SMS, tried to work it out. We couldn't work it out, and we've never had a sample with enough concentration to do accurate mass spec on it to get an idea of what we're seeing, because we've done fraction collection and tried to collect at the time, but we still can't see how that occurs. So last week I ate 3 packets of these, and I collected my own urine for 3 days, but I didn't see this peak. And the worker has subsequently provided us with a second sample where he hasn't eaten any seaweed and he doesn't have the peak. So we are trying to replicate this peak in this worker and hopefully in other volunteers who would like to eat the seaweed that's sitting on a box on a desk in our office. And we might find out a little bit more. We know that seaweed contains arsenic. We know there's been quite a lot of work done on it. But the main reason for needing to know what this peak is that we can better interpret exposure. One concern is always that this peak has excreted from a worker as part of a workplace exposure. In this instance, I don't think this is the case, but we need to be sure, and it will help better with our interpretation if we can understand more about it. So in summary, wanted to give you a flavour of the arsenic speciation that's undertaken in our lab that we do routinely with a micro-LC ICP-MS method. It provides more information about exposures, both environmental and occupational, rather than just having a total or an extracted arsenic concentration. We've established our own background ranges, and they compare well actually with background ranges that have been cited by both the Canadian and the American background level studies, biomonitoring studies, where they collect lots of more samples than we do. The workplace exposures in the UK are generally well controlled, although we do see instances of exposure in manufacturing industries, and we have seen it in overseas samples, so not in UK samples, and that warrants further investigation. And we're working to elucidate the second unknown peak that we see, and we have a nice PMSMS where we'll be trying to pre-concentrate that. Hopefully someone can make it from seaweed, and we'll be hopefully coming back to you with more information about what that peak is. And so I thank you for listening, and I try and go back to the meeting. Let's see. Okay, so okay, and we'll try and get everyone back on and see if there are any questions. Let's do that. Hi, Priya.
Hello. Sorry for
Hi,
the
everyone.
little technical glitch.
It's okay. It's difficult, isn't it? I found that my control of this actually got in the way of my presentation. Okay, so let's see what questions we have, if we have any questions. I can't see actually that there are many questions. Have you guys seen any questions? Yeah, there. Just it's a little odd to see the questions. Let's just go down. Julian, I think there was a question just about was it about the fastest method? A race to the quickest method, I think, was using. Oh, that was from you, Julian. Sorry. I can't see that there are any major questions that anybody has. Let's go back. Priya, I have one for you. It was really interesting to appreciate that, because I see it from the other end. I see it from the urine side and not from the food side, but it was quite interesting to appreciate what an impact the food has. And we don't ask about wheat, and we don't ask if people eat roti bread or chapatis, and I guess that's a real factor, isn't it?
Well, I guess I won't be expecting the wheat. If you're talking about your study population in UK, then I wouldn't consider it as something to be worrying about. Of course, in UK, we are still looking into arsenic exposure from rice, and you have been involved in studies perhaps as well. So where arsenic from rice might be arrested in UK population, but not from the wheat. If you remember, I mentioned that we normally in this study population, they were soaking their wheat in contaminated water, which could be the reason that the flour, which is used to make the breads, the homemade breads, they got the arsenic picked up in it. Otherwise, wheat should be having much, much, much lower arsenic compared to the arsenic in rice.
Okay. The only question we've got is a lovely comment from Ken Marcus, and he says, "Great job, folks. We're interesting and informative. Bravo to the RSC ASG. Cheers, Ken." So it means the questions are working. So if any of the 109 people still online would like to ask us a question, we're here and I can see them. So it would be lovely to hear from you. Do either of Laurie or Julian, do you have any questions for anybody or any comments? Sorry, Julian, let me just it just says you're self-muted, Julian. Sorry. Can you unmute? Okay, are you there?
Yes, now I'm unmuted. Thank you.
I can see.
So I had a question for Laurie about the atmospheric deposition. You know, I've wondered for a number of years as to whether the reason that we're not seeing any decrease in the arsenic concentration in rice grown in the United States is that there is some as yet unknown mechanism by which the arsenic concentration in the soil is being replenished. Because I would have thought as the years go by and we're not adding any arsenical pesticides to these fields, there would be a kind of sort of natural phytoremediation process going on, and we would see a decrease in the concentration in the US rice. Although the data is limited, I'm not really seeing that there is such a decrease. And so I wondered whether you have any thoughts about whether atmospheric deposition of arsenic on US rice growing paddies could be a significant contributor to the fairly elevated concentrations we see in US rice.
Laurie, sorry, can you not? Sorry, it says self-muted again.
Okay, now I can
Sorry.
talk. Thank you very much.
Sorry, it willy-nilly changes its mind.
That's okay. I think that's a really interesting question. I know less about the arsenic cycle in America. I've looked much more in Bangladesh and India. But yeah, that's a really interesting question. So what we're seeing with the rain that falls, the concentration of TMAO, or the concentration of all arsenic, is a ready labile source of arsenic, and it's very similar to the uptake in rice. I think an interesting way to look at it could be looking at a drainage basin level. If you consider the massive drainage basins in South Asia, it could be considerable amounts of arsenic falling. And in terms of America, like where arsenical pesticides haven't been used for a long time, it would be interesting to look, to see what the deposition of arsenic is. The thing is, there's just very, very little data, especially speciated arsenic. There's just very, very little data. But I think that the meteorology modeling that I used was absolutely essential for the work we did, because like the deposition won't be uniform. It will vary very much by prevailing winds. Either marine produced arsenes or industrial, inorganic arsenic.
So next time you're writing a research proposal for funding, throw in the USA as a country of interest.
Yeah, absolutely. I mean, there's data for. I mean, obviously, there's a lot of data for arsenic in rice from the US. It's worth mentioning as well that inorganic arsenic in rainwater and atmospheric deposition isn't necessarily industrial or geogenic, because with UV degradation of methylated species in the atmosphere, so actually you have quite a ready breakdown from trimethyl arsenic oxide to inorganic arsenic. So that rain that falls that you collect, you can't immediately determine what fraction is natural and what fraction is not. So there's a lot of complex issues that.
So we have got a question. It's a general question, wanting to know what the background arsenic contaminations in the lab environment could be. What sources of contamination could there be, and how do you control the limit of detection? For me, we started quite early on trying to get our blanks lower and lower, and we have to, you use plastic volumetric flasks to make your standards. You make all your samples and your mobile phase in plastic bottles, and you use filtered water, and you check all of your mobile phase for arsenic contamination. We went through a stage where the batch of ammonium carbonate we used changed after about 5 years, and it took us quite a while to find a as clean ammonium carbonate to use again. What about you guys? Have you got any comments on contamination in the lab?
Much the same as you, although it sort of hurts my budget. I buy arsenic-free reagents when necessary. We used to sub-boil our own acids, but we stopped doing that a few years ago. And so we shell out for the purest grade nitric acid, which is what we use most of in terms of our acid digestions or acid extractions of rice. So it's blank contamination is always a problem for us. But it's reagents. We don't have any sort of other sources of contamination that we're aware of.
Yeah, I think nitric acid is the big one. So one easy way to reduce is to use less nitric acid. So for the rainwater speciation analysis, I didn't acidify the samples. I tried to use as few stages as possible. So really, I wanted it to go from sky to instrument with as few steps as possible to reduce any chance of contamination. And the samples weren't acidified, to make sure that nothing was introduced. But we did add peroxide to everything, but that's not a big source of arsenic.
And we've also got a question about what about sample pre-treatment? Does anybody do any?
Well, I can take that in terms of the rice analysis that we've been doing. Like many other research laboratories, we've sort of honed in on the dilute nitric acid extraction, and we use a Mars CEM microwave assisted system using pressure sealed vessels with the dilute nitric acid. Of course, speciation analysis, it's always a concern as to whether your sample preparation is going to transform the species. But this dilute nitric acid has been looked at by a number of research groups around the world, and so I think that we're pretty confident that at least in the presence of the thiol type compounds that are released from rice, the oxidizing potential of the nitric acid is sort of balanced by the reducing potential of the thiols from the phytochelatins. And so you don't see any significant redox change between arsenic 3 and arsenic 5. And to convert methylated arsenic to an inorganic arsenic, you need pretty aggressive conditions. So there's absolutely no danger of that into conversion for us.
Yep. Priya, I've got a question for you. Can you confirm that the exposure from wheat is more due to contaminated water?
Well, this is one of the hypotheses, and we will be testing it, but we can confirm it on the basis of that the arsenic concentrations in the grain, as reported in literature with the paired flour samples, has often been found to have higher compared to the flour. So as I mentioned that during the process of the grinding, the barn is removed and arsenic get lowered. And this has been noted every time the paired samples for arsenic in grain and flour has been looked into. For ourselves, we didn't look into the arsenic in the grain before and after soaking. We were just looking into the arsenic in grain and also arsenic in the paired flour samples, which they grind at their own place. So the only reason we can see that the contamination is coming is from during the grinding process. And this is what we have hypothesized to say that it could be the contaminated water. Also, there is a possibility that it is the grinder, or it could be some environmental contamination. These areas are all contaminated, and these people do many of a process in open air. So there is a possibility that there could be some soil contamination and etc. coming from the environment as well. But that needs further investigation.
And just as a follow-up question from that, we've been asked, some UK soils do have a high natural arsenic content. Do we know anything about crop arsenic content in the UK?
I have to say that apart from rice, there hasn't been many other crop which has been an accumulator of arsenic. So we know that it is rice which can accumulate arsenic easily. That said, we do find arsenic concentrations at some low level, like in wheat, as I have shown, apart from these areas where there is some other reason, but also in some other vegetables. So some root vegetables can acquire arsenic. I would imagine that the concentrations of arsenic in the soil and the type of crop cultivated in UK and their base levels has been documented in the EU Food Service. So we know what are the baseline concentrations of arsenic in different food products produced or consumed in UK, both produced and both imported. And so based on market-based service. Yeah, I wouldn't be too worried. That would be my answer.
I do know that we once did some samples from a woman who was growing her own strawberries, and there was arsenic in the strawberries, but there wasn't any arsenic in her urine. So whether or not we just didn't capture it, but the concern was that it came directly from soil there. I've had a comment that the peak that I see in the urine from people eating seaweed might be dimethyl arsenicyl acetic acid. So I've written that down, and I will certainly go away and look that up. Thank you. Jackie, could the unknown peak be arsenobutane? Because arsenobutane is quite common. No, arsenobutane is our first peak. And then the contamination. I've got all of them. Dr. Mondal, after detecting arsenic in foodstuffs, what interventions can be taken? Does anyone attempt to remove arsenic from irrigation water?
This is a very good question, and we have been trying to put our research results to the policymakers. But you have to understand that the studies where I'm being looking into this arsenic from food exposures are really under resource poor setting. So both Bangladesh and India are already still struggling to cope up with arsenic exposure from drinking water. And to my dismay, every time we talk about the irrigation water, it has been nobody's area. So the government says to provide with safe and arsenic-free drinking water is a priority, but not the irrigation water, because that doesn't come under the drinking water supply schemes. And the irrigation department, they are not much concerned with this problem yet. We are looking into some other remedies. So for example, there has been a lot of research, and from my group as well, to look how arsenic in rice can be removed. And for example, if you cook rice in excess water and then drain the water, there is a good amount of percentage of arsenic that can be removed from grain to cook rice. And then we have been advocating in these areas that if you are grinding your wheat, make sure if you have to soak it in water, it should be safe water. So if in my presentation, I have shown you that in this study population, there were a good proportion, almost 75% and above, was using clean or safe drinking water, at least less than the WHO guideline of 10 ppb for consumption, so for drinking. But they may not always try or buy clean water for cooking. So that is what we are advocating, to reduce arsenic exposure due to cooking, because at the end, it is the cooked food which is consumed. So cooking method is one way, grinding in clean water is another way, and at the same time, we are saying that cook your food in clean and safe water. So this is a couple of things that at household level, we are asking people to do to get rid of some percentage of arsenic from food.
Okay, I'm aware of the time. We're slightly over time, but we have about 5 more minutes before we get cut off. I was just going to finish with a final question for Julian, if that's okay.
Sure,
it
go
says
ahead.
there is a real niche for AFS and hydrogenation. Can you comment on the role of a photolytic reactor in such systems?
Maybe. So we don't have any direct experience of using photochemical generation. The world expert, I think, is Ralph Sturgeon at the National Research Council in Canada. And so any article that comes from his group, or at least it has his name attached to it, I think could be taken as a reliable indicator of the possibilities for photochemical generation. You need some kind of additional reagents other than just borohydride. So you don't use borohydride, you use UV light and formic acid or some other organic compound. I have to say that I'm not convinced that photochemical generation's really got anything to offer over what we might call conventional hydride generation. Clearly, if you want to do speciation analysis, you have to make the reaction chemistry selective, which is well known how you can do that with borohydride chemistry. You just control the acidity in order to promote or suppress the chemical vapor generation of one or other species. I don't know enough about the literature to know how easy that is to do in terms of photochemical vapor generation. So a long-winded way of saying I don't really know enough to make a sort of detailed evaluation for you, but well worth looking at, I think, if you're not afraid to do a little bit of your own instrument building to get the technique to work.
Julian, just finishing up, it's not really a question, but Steve Hill has commented, enjoyed your talk and agree with most of your comments on choice of analytical approach. However, probably worth saying that for some of the matrices, e.g. marine products and mushrooms, the complex speciation requires the use of Hplc to separate species such as ozonosugars.
Absolutely, don't disagree with Steve on that. Remember, everything I said was within the context of inorganic arsenic species in rice. If you've got a more complicated arsenic speciation set or mixtures of anions and cations, then you need to really consider chromatography as your first line of attack.
So what I'm going to do, there are still some more questions coming through. I'm going to copy the questions and see if we can reply to them offline after, I think is the best way to do it. And Laurie, there's been a comment about what a great haircut you've got.
Lockdown.
Some of us can't get out to get our hair cut yet.
I'm not. No, we can't either. So I imagine it's not a hairdresser trip, Laurie, maybe. So it all remains to say thank you very much to our speakers today. I'm just going to thank you for bearing with me on the technical parts of my disastrous flicking between you all. Yeah, it's not it's not the easiest on here. And every time I clicked to give you all the speaker, it told me that you had, and then you couldn't. So I apologize. But thank you so much. I really appreciate your time.
Thank you very much.
All of the comments coming through, they really appreciated the presentation. I thought they were very good. So thanks, guys. So I'm going to unshare your screens. Let's go with that. And so once again, thanks to Professor Julian Tyson, Dr. Priya Mundal and Dr. Laurie Savage. I would like to just draw your attention to our next one of these virtual meetings, which will be on the 12th of May, called B is for Biomonitoring. The talks there will be from Robert Jones at the CDC in Atlanta, talking about biomonitoring and whether in relation to the Ian Haynes biomonitoring cohort that they analysed there in their lab, from Adam Laycock at Public Health England, talking about lead isotope ratios in children, and Dr. Elizabeth Leese from the Health and Safety Executive, talking about a HBM4EU project looking at hexavalent chromium. I hope that you will all join us then. If you have any comments, please feel free to email me directly at jackie.morton@hc.gov.uk. And I thank you all for attending. Thank you.